need to use this for questions. Remind me, because otherwise the people online can hear us.
Okay, well, thank you. And thank you to the organizers for the invitation. Some of you may have heard this in Lumini, and it is not particularly related to, well, it's not at all related to randomness. But I don't think I'm alone in that. It is related to one of the other talks at this workshop. Well, let me give you, first of all, an outline of what we're going to talk about today. This is the talk that's going to be about the enumeration degrees. So we'll quickly review the enumeration degrees. We'll talk about minimal subshifts, because it was a question that came out of the study of minimal subshifts. That was the original motivation for us studying the cototal sets and degrees. And we'll introduce uniform introenumerability, as well as cototality. We'll, let's see, does this work? Ooh, yeah. We'll talk about enumeration pointed trees and McCarthy's characterization of cototality, and relate this to uniform introenumerability. And then describe the recent work. So we'll do, this is a lot of background, so that you can describe fairly recent work with Go, Jacobsen-Grocott, and Soskova. And then get into the proof that there's a uniformly introenumerable set that is not of cototal degree, all of which will make sense by the time we get there. All right, so first of all, the enumeration degrees. You are all, I hope, familiar with Turing reducibility. Friedberg and Rogers introduced enumeration reducibility in 1959. And informally, a set A is enumeration reducible to a set B if there's a uniform way to enumerate A from an enumeration of B. There's a uniform procedure that, given an enumeration of B, a listing of B in any order, produces an enumeration of A. I will say this. I'll say something about this later. That uniformity can actually be dropped. It's enough to say that every enumeration of B is Turing above an enumeration of A, which is kind of interesting. And I'll just mention that later. It won't have anything to do with the talk in general. So what's happening here is that you're using information about membership in B, but not non-membership, only positive information about B to produce positive information about A. And all enumeration reductions actually can be given this form, that A is enumeration below B if there's the CE set W such that, so W is a set of axioms such that A is a set of all N for which there is an E, such that NE is an axiom in W, and DE, where DE is the e finite set in a canonical enumeration of finite sets, is a subset of B. So I see DE enter B eventually, if it is a subset, and I say, aha, N is an A. I don't know why I'm explaining this in so much detail, but I can't really necessarily assume that everyone here has seen enumeration reducibility before. The degree structure induced by this reducibility is called the enumeration degrees. It is an upper semi-lattice with least element, which is the degree of all CE sets. And as we'll see, it is actually related to the Turing degrees as follows. A is Turing below B if and only if A join A complement is enumeration below B join B complement. Basically, if I make all the positive and negative information about B and A positive information, then enumeration reducibility is enough. That I can get all the information about A, given all the information about B is the same as Turing reducibility. This gives you a natural embedding of the Turing degrees into the enumeration degrees by sending A to A join A complement. That induces an embedding that preserves order and least upper bound. So you can view the Turing degrees as a substructure, a proper substructure of the enumeration degrees, and we call a set A total if A complement is enumeration below A. So the positive information about A somehow already knows the negative information. And that's equivalent to A being an enumeration equivalent to A join A complement. An enumeration degree is called total if it contains a total set. And the image of the Turing degrees under this embedding is exactly the set of total enumeration degrees. So the substructure that looks like the Turing degrees, we call that the total degrees. And a degree is total if and only if it contains a set of the form A join A complement. It's easy to prove that there are non-total enumeration degrees. A sufficiently generic set is non-total, and by sufficiently generic, I actually mean one generic. You don't need a lot there. Okay, so we have our introduction to the enumeration degrees. Now, much of the rest of the content of this talk was originally motivated by a question of Emmanuel Jeandel. He's a symbolic dynamicist, and he sent an email to ask, if I have a set A such that A is enumeration below A complement, what can be said about the enumeration degree of A? I'll explain why he was asking that question, but our answer was immediately, I don't know. He sent that email to me. I asked Maria Soskova, who is much more likely to have a good answer to that question. She didn't, and we said, we don't know, and set about studying that property. We called it cototality. We said a set A is cototal if A is enumeration below A complement, because it is, remember, I said it's total if A complement is enumeration below A, this is total. So flipping that around, it makes some sense to call that cototal. And an enumeration degree is cototal if it contains a cototal set. Now, I should say that the word cototal had been used already by Solon, and he used it slightly differently. He actually used it in two different ways himself. And all three of those uses are in fact distinct, but they're all very related. And so we kind of hijacked the word for what we thought was the most natural version of this kind of family of properties. And we, like I said, we studied this, and in a later paper, confused by publication date, but definitely a later paper, we showed, for example, that the cototal enumeration degrees are a dense substructure of the enumeration degrees by relating cototality to something that had already been studied in the enumeration degrees, having a good approximation. All of this was fun and great, didn't really answer Jeandel's question beyond some enumeration degrees have this property, all total enumeration degrees have this property, all total enumeration degrees are cototal, and not all enumeration degrees have this property. Beyond that, I don't think he cared about any of the answers, any of the things we proved. But I do want to say, why do all total degrees? Why does total imply cototal? For degrees, at least? Well, because A join A complement is cototal. Cototal. I mean, it's obvious, A join A complement is obviously enumeration below its complement, which is A complement join A. Okay. So why was Jeandel interested in sets with this property in the first place? Like I said, he was studying symbolic dynamics. And so I'm going to give you a little quick introduction to symbolic dynamics. Just the bits that we need. The shift operator is a map from 2 to the omega to 2 to the omega that just erases the first bit, just lops off the first bit of the sequence. And a subshift is a subset of 2 to the omega that is closed and shift invariant. A minimal subshift is a subshift such that there's no non-empty proper subshift. Okay, so these are nice. These are interesting objects. Minimal subshifts are interesting objects. There's some trivial ones. You take any sequence that just repeats, so that when you apply the shift operator, it'll just give you a finite orbit. That's minimal. It's not very interesting. But there are interesting minimal subshifts, and every subshift contains a minimal subshift. So the languages of a subshift is the set of words that apply a set of strings, binary strings that occur as subwords of a subshift. Now, usually, actually, if you've ever seen any symbolic dynamics, you'll know that the language is not usually what people look at. People usually look at the complement of the language. They look at the words that are avoided, because the subshift is determined by the avoided words, and that's usually where you should be putting your attention. But for minimal subshifts, actually, the language is quite relevant for the following reason. C is minimal if and only if, okay, for every x in C, the orbit of x is dense in C. Well, that's one direction that's not hard to see at all. You take any x, you look at its orbit, you take the closure of the orbit, that is now a subshift. If that's not the whole thing, then you didn't start with a minimal subshift. And the other direction isn't hard either. And, well, the orbit of x being dense means that x contains every possible subword that appears in the subshift at all. So in fact, every element of C is minimal if and only if every element of C contains all the words in LC. So the language is actually really relevant for a minimal subshift. This isn't hard to see. I proved some of it for you there, and the rest isn't that hard to fill in. But it's nice. Now, assume C is minimal, then every x in C can enumerate the language. Just look at all subwords of x. Okay. And conversely, from an enumeration of the language, we can compute an element of C. Different enumerations will give you different elements, but basically just start with your first subword. You're going to find some longer subword eventually, and some longer subword than that eventually, and you're just building an element of C. So these are actually equivalent. Oh, sorry, what's equivalent? A Turing degree computes a member of a minimal subshift if and only if it enumerates L of C. So, and in fact, for non-trivial minimal subshifts, any Turing degree that computes a member of the subshift also contains a member of the subshift. And the trivial ones were the finite orbits. Okay. So therefore, the degrees of members of a non-trivial minimal subshift C are exactly the total degrees above the enumeration degree of the language. Okay. Any degree that enumerates this language computes a member, and that's a characterization. So it'd be nice to understand these enumeration degrees, maybe, if you want to understand how hard it is to compute a member of a given minimal subshift. Well, that language, the enumeration degree of the language of a minimal subshift, isn't just any enumeration degree. It's going to be a cototal enumeration degree. So, and that's what Jeandel noticed. It's not too hard to see. If C is a minimal subshift, then the language of C is cototal. And basically what we can do is use an enumeration of, so if we have the complement of the language, like I said, that's usually what you think about when you're thinking about subshifts. You can use the complement of the language to kill off all non-members of the subshift. Basically, the subshift is pi 0, 1 relative to that set in the enumeration sense. Okay, that didn't help. But given enumeration of the complement of the language, you can prune all the branches that do not extend to elements of C. And by compactness, if tau is in the language, it has to be in every element of C. By compactness, you'll eventually see that all remaining paths have tau as a subword. I'm not sure how much sense I'm making because I really am quite jet lagged. So please feel free to ask questions. I wouldn't be able to follow this talk. So a similar compactness argument shows that if C is a minimal subshift, then there is an enumeration operator such that given any infinite subset of the language, the enumeration operator returns the whole language. Okay. So that's very similar to the argument above. Neither of these is too hard if you realize that this is something you want to do. Once once stated, is not that hard. They were really interesting observations, though. We call the second property uniform. Sorry. Okay. We call the second property uniform introenumerability. That any infinite subset of the set, from any infinite subset of the set, you can enumerate the whole set, and uniformly so. And of course, this is cototality. So the language of a minimal subshift is cototal and uniformly introenumerable. Let me say a little bit about introenumerability. A set is introenumerable if for every infinite subset of A, set A is introenumerable if for every infinite subset of A itself is enumeration below S, and if that is witnessed uniformly, then it's uniformly introenumerable. We did not introduce this definition. Well, we kind of did, because we got it wrong, but actually, Carl Jacobsen in 1968 defined uniform introenumerability by asking that that A be CE in each of its infinite subsets. I don't feel too terribly guilty about, we should probably change the term, but at least I don't feel too terribly guilty because the uniform versions of these two coincide, and I don't know about the non-uniform versions. But the difference between being CE in an infinite subset and being enumeration below an infinite subset could, that is different. So, but we'll mostly be talking about the uniform version where it's not actually different. Greenberg, Harrison, Trainer, Pate, and Turetsky showed that every uniformly introenumerable set has a uniformly introreducible subset. And Dan will be talking about that on Wednesday. Well, I don't know how much I'll talk about that. I'll be talking about the work in this paper on Wednesday. So go to his talk if you find this at all interesting. Okay, so taking stock. We care about cototality and introenumerability because of this email from Jeandel. Well, we left some questions open. First of all, we just kind of ran off and proved a bunch of things about cototal degrees, not really thinking about the original motivation for the question. Are the degrees of languages of minimal subshifts exactly the cototal degrees? Or, for example, is it special that languages of minimal subshifts are also uniformly introenumerable? How do the uniformly introenumerable degrees relate to the cototal degrees? Okay. Well, my student Ethan McCarthy showed that every cototal enumeration degree is actually the degree of the language of a minimal subshift. So in fact, the cototal degrees are the right notion if you're interested in languages of minimal subshifts. And this also shows that every cototal degree is uniformly introenumerable. Every cototal degree contains a set that is not just cototal, but also uniformly introenumerable. Now, that conclusion doesn't require this full theorem. There's an intermediate step where you already have this conclusion, and that's the step from cototal to the cototal degrees to the degrees containing e-pointed trees. And McCarthy's proof passes through that step. So I'm going to talk a little bit about e-pointed trees. I'm going to bring all of these different classes back together in a diagram in a little bit So, you know, hang in there. Actually, this relates to another email we got. And honestly, if you have any questions about enumeration degrees, feel free to send us emails about them. We enjoy that. We get papers out of it. Antonio Montalban, he didn't actually present this definition in writing. This notion is implicit in his first book on computable structure theory. But he wrote us an email asking, what can we say about the enumeration degrees of e-pointed trees? And an e-pointed tree is a tree in, say, unless otherwise specified, 2 to the less than omega, that has no dead ends, and every infinite path through the tree enumerates the tree. Okay. No, paths are total objects, so actually CE in. It's equivalent because we treat paths as total objects. Yeah. So we consider several variations. We could look at trees in omega to the less than omega. We could require that that paths uniformly enumerate the tree, that there's a fixed operator that does it, fixed, in this case, CE operator. And we could allow dead ends if we were, you know, really going nuts. Okay. Now, very simple compactness arguments, like the ones from a couple of slides ago, well, the ones from a couple of slides ago, show you that uniformly e-pointed trees are in fact cototal and uniformly introenumerable. And that's not unrelated to the fact that languages of minimal subshifts have these properties, because if you take a minimal subshift C, which is the set of paths through some tree T with no dead ends, then T is uniformly e-pointed. So these are related. And what McCarthy did in his proof is he started with a cototal degree, built an e-pointed tree in that degree, and then from that e-pointed tree, a uniformly e-pointed tree, in fact, and then from that uniformly e-pointed tree, he got the minimal subshift. But you don't actually need that last step if you're just interested in cototality and introenumerability. Okay. So why was Antonio interested in these things? His motivation came out of commutable structure theory. And he was looking at the spectrum of accountable structure. Just proving some basic results mostly, because this is in his first book on computable structure theory. So if you have a structure M, the spectrum of M is the set of all, I guess, degrees A, such that A computes a presentation of M. A presentation, it computes a structure on omega that is isomorphic to M. Here I wrote computes for non-trivial structures. Computes is the same as contains, blah, blah, blah. Okay. So he was interested in this, and it's known that there are some limitations on the spectrum, the possible spectra of structures. For example, it's known that you can't take all degrees that either compute the set X or the set Y, as long as X and Y are incomparable. Now, that I mentioned this specifically because this is kind of prototypical for what this theorem is saying. That this theorem is saying that if a structure spectrum is a Turing upward closure of an F sigma subset of 2 to the omega, then it is an enumeration cone, the set of Turing degrees above some fixed enumeration degree. Well, in this case, you can do better. But basically, look, the pair XY is a closed set in 2 to the less than omega. 2 to the omega, sorry. The Turing upward closure would be the spectrum, and this is not an enumeration cone, so not possible. And basically, what I think Antonio was doing here was trying to take that technique, the technique used to prove something like this, that this is not a structure spectrum, and push it as far as you could. Okay. So in fact, it must be the cone above the enumeration degree of an e-pointed tree. So not just any enumeration cone. And furthermore, the converse holds, with the structure witnessing it as being the e-pointed tree itself. Okay. He kind of wrong-footed us, because the same is actually true for F sigma subsets of omega to the omega and bare e-pointed trees instead of Cantor e-pointed trees. And it really took us for a long time to realize that it wasn't all just the same theorem, that it actually mattered whether you were looking at F sigma subsets of bare space or Cantor space, and that threw us a little bit. So, I mean, I'm not blaming you, I should blame us. We were thrown a little bit by that. So we really thought by understanding e-pointed trees in Cantor space that we understood these enumeration cones, and we didn't think about e-pointed trees in bare space. Okay, how slow am I going? Slow. Okay. So McCarthy, like I said, proved that, and this is not something I've already stated, I've alluded to. He proved that every cototal enumeration degree contains a uniformly e-pointed tree in 2 to the less than omega. He also proved that uniform can be dropped or not, and you can have dead ends or not. So in fact, of the 8 versions of e-pointedness, 4 of them collapse to cototality, and they still don't give us anything about bare e-pointed trees. Okay. So we saw this question about introenumerability, uniform introenumerability, and how it relates to cototality. We know that every cototal degree contains a uniformly introenumerable subset, but we don't know if uniform introenumerability implies cototality, for example. Well, it kind of comes close. If by that you mean the wrong thing, I guess. Given any infinite set I, let Ti be the tree of subsets of I, and I specifically mean that F is a path through Ti if and only if F is an enumeration of a subset of I. In other words, an injective function whose range is a subset of I. I want injective just so I can make sure that it's giving me an infinite subset. Okay, so this is tree of subsets. Note that this has no dead ends because I is infinite. And also note that if I is uniformly introenumerable, then Ti is uniformly bare e-pointed. Every F path through Ti enumerates its range, and its range, because I is uniformly introenumerable, enumerates all of I, is enumeration above all of I. And yeah, if we're assuming uniform, that's uniform. If we're not, it's not. But what it gives us is every path through the tree enumerates I, is enumeration above I, and I is enumeration above Ti. You can enumerate I, you can enumerate the tree. And that proves that uniform introenumerability implies uniform bare e-pointedness, degree-wise. So in the enumeration degrees, cototal is equivalent to uniformly e-pointed, which implies uniformly introenumerable, which implies uniformly bare e-pointed. But we've made a big jump going from e-pointed in Cantor space to e-pointed in bare space, because these implications are strict. And here's the diagram. So total implies cototal, which has this characterization in terms of e-pointed trees in Cantor space in 2 to the less than omega. and really has 4 versions of that. Who cares? Cototal implies uniform introenumerability. That implies uniform very pointedness. And then there's these things up here I haven't talked about. But basically, this part I've definitely talked about. And also this implication if we drop the uniformity. And then these 2 dotted implications are obvious. Whether they reverse, we don't know. The red arrow is open. It's not known if being introenumerable implies being uniformly very pointed. We think not. If not, then the dashed arrows are also strict, but we don't know. Everything else is resolved. Okay, so what's this stuff up here? I want to say a little bit about that. Okay, this is a diagram I'm going to come back to, and I will talk about why this arrow. Nope, I will talk about why this arrow is strict. Why uniform introenumerability is weaker than cototality. That's one of the main results in this joint work with Go, Jacobsen-Grocott, and Soskova. Okay, but let me talk a little bit about very pointed with dead ends, because it is a really weak notion. Oh, but first I have to talk about what is hyper-cototality, and so what is hyperenumeration reducibility. In 78, Sanchez introduced hyperenumeration reduction as a higher version of enumeration reduction. Here's the definition. It looks a little terrible the first time you see it. A is hyperenumeration below B if there's a CE set W, a set of axioms, such that A is a set of all n, such that for all paths in bare space, F, basically this says if you take the enumeration reduction given by the oracle enumeration reduction given by W relative to F, then n is in the output and is output by that reduction. So one way to think about this is I'm doing enumeration reduction relative to all paths, taking the intersection of all of those results, and that's this A. I'm going to give you a different way of thinking about it, but that's basically what's written down here. Because everything from here on looks like enumeration reduction, except that I have this silly sigma there. Okay. So for each n, consider Tn, subset of omega to the less than omega, whose complement are the set of taus such that I have basically along tau I've seen n enter the oracle enumeration reduction. So right. So Tn is a tree, and just as what I've written here, Tn is enumeration below. Sorry, Tn complement is enumeration below B, uniformly in n. Okay, and n is an A if and only if there's no Tn is well founded. An infinite path witnesses that there's some F up in this definition for which you don't have a sigma and don't have an E, with such that sigma n E is an axiom in W and D is a subset of B, right? An infinite path through Tn is exactly a witness that n is not in A. Okay. And the reason I've written these 2 things down is because A is hyperenumeration below B if and only if there's such a sequence of trees. You can forget this definition if you want, and just say there's a sequence of trees whose complements Tn, whose complements are enumeration below B, and the nth one is well-founded if and only if n is in A. And here, and you can see, because I mean this is all about well-foundedness now, why this is a higher version of something. Enumeration reducibility, maybe? I don't know. Maybe. It does seem to fit pretty nicely into the analogy that this analogy that between Turing reduction, CE relative to, and enumeration reduction on the one hand, hyperarithmetic reducibility, pi11 relative to, and hyperenumeration reduction on the other hand. There's a pretty good analogy. For example, A is hyperarithmetically below B, hyperarithmetically reducible to B, if and only if A join A complement is hyperenumeration reducibility, reducible to B join B complement. We really only used, in the definition of HE reduction, we really only use positive information about B to get positive information about A. Arguably. Okay. And also, A is pi 1 in B if and only if A is hyperenumeration below B join B complement. These are the kinds of analogies you would want to hold. Not everything works out perfectly, though. And here I'm advertising a result of Maria's student, Josiah Jacobsen-Grocott. So Selman's theorem, a really important result, if you're studying enumeration degrees, says that A is enumeration below B if and only if for all x, if B is CE in x, then A is CE in x. This is a really beautiful result. It does a few things for us. One of them is it defines enumeration reducibility entirely in terms of being CE relative to Turing degrees. Well, another way of thinking about that is it says that an enumeration degree is determined by which total degrees are above it. And in fact, notice that there's no uniformity in this implication. So remember when we the very first slide with content on it, where I said that you can drop the uniformity from the definition of enumeration reduction? Well, this is why. On the other hand, Josiah showed that there are sets A and B such that A is not hyperenumeration below B, but for all x, B being pi 1, 1 in x implies that A is pi 1, 1 in x. So the analogy is broken in this case. Selman's theorem does not hold for hyperenumeration reducibility. And it's worse than that in some sense. For the A and B he constructs, this is true uniformly. So even a weaker version of Selman's theorem doesn't carry over into the hyperenumeration degrees, which is, I don't know, a little surprising. Okay, so that's an advertisement for Josiah's work. Hyper-cototality. Yeah.
Analogy between file 1 and RE, file 1 is the same as signal 1 over the admissible.
Mm-hmm.
So the x goes to L omega 1.
Mm-hmm.
All that.
Yeah.
Is there something that are companion? Does that work with the companion?
I don't know. I mean, that's yeah, that's a good question. And I'd be happy to talk about that after the talk. I mean, I would say that yeah, I would be interested to know like why we have this breakdown here, and if it's a sign of something bigger.
Just make this set in the definition of enumeration reducibility pi 1, 1 rather than the same.
No, Sanchez showed that was equivalent. Very good question. Yeah, that's equivalent. Okay. So hyper-cototal is what you would think at this point, that A is hyperenumeration below a complement. And an enumeration degree is hyper-cototal if it contains a hyper-cototal set. This is equivalent to only containing hyper-cototal sets. It's actually, being hyper-cototal is actually an enumeration degree notion by itself. You don't need to close under enumeration equivalence, but whatever. Okay, so an enumeration degree is hyper-cototal. We showed if and only if it contains a uniformly bare e-pointed tree with dead ends. So if you're in bare space and you allow the tree to have dead ends, whether or not you allow uniformity, you're really just capturing hyper-cototality. Now, all pi11 sets are hyper-cototal since they are the least hyperenumeration degree. The least enumeration degree is all CE sets. The least hyperenumeration degree is all pi11 sets. So to even talk about something that's not hyper-cototal, we have to go beyond the hyperarithmetic sets. On the other hand, no 3 generic is enumeration equivalent to a Berry-appointed tree. So not containing a Berry-appointed tree, that can already happen in the arithmetic sets. The degrees of our enumeration degrees of arithmetic sets. I have to say, like last night, I realized we never really wrote that proof down. What we actually have is a construction of an arithmetic set that is not enumeration equivalent to a Berry-appointed tree. So I should. This is what I really should claim. It's the sort of construction that should morally be generalized to that, but no one's bothered to work through. There are some details. There are some helper sets being built that are paths through trees showing that they're not Berry-appointed, not E-pointed. So you'd have to make sure that actually works out. But at least containing a Berry-appointed tree can fail for arithmetical enumeration degrees. And those are all hyper-cototal. So we know that hyper-cototal does not imply Berry-appointed. And in fact, like this is so far away from, this is so much weaker than that. There's a big gap. This can fail for arithmetic. This is trivially true for hyperarithmetic. Okay, so I spent a long time telling you about these things, but they're too far away. All the action is really happening here. Well, there's a uniformly introenumerable set that does not have cototal degree. That's showing that this implication is strict. That's our first main theorem. And our second main theorem is that there's a uniformly Berry-appointed tree that does not have introenumerable degree, showing that this, well, actually showing not just that this is strict, but in fact that this is false. That this does not imply that. Okay, a little bit stronger. Who cares? Well, I mean, it shows both that this is strict and this is strict, and does a little bit more than that. Okay. So now would be a good time to ask any questions, because I'm just going to dive into a forcing notion. If you don't, well, you brought it on yourselves. All right. So I want to say a few words, a few slides worth of words about this proof, that there's a uniformly introenumerable set that does not have cototal degree. And we build this set I by forcing. So assume, first of all, that we fixed a suitable enumeration operator psi that will witness that I is uniformly introenumerable. And we want psi to be nice. It must behave well with respect to finite sets. Let's say it takes the empty set to the empty set. If S is a finite set, then so is psi of S. And this is where things get more interesting, if psi of S is a subset of T, where S and T are finite, then there's some X, in fact infinitely many, such that psi of S union X is T. We can always grow psi however we want, and not just for one choice of S and T, but under reasonable consistency assumptions, which is why this is not the right way to define psi. It's easier to define psi differently and the consistency is automatic. This extends to any finite sequence of pairs that, again, aren't like logically impossible. Okay, so we want this nice enumeration operator, and we're just going to fix that, and that will witness uniform introenumerability. So then what's the forcing notion that we're going to use to build I? Well, it has the form G, that's for good, bk through b0, Those are levels of badness. And L for labeling. And it has to satisfy the following 7 conditions. So sorry. Okay. These are all disjoint finite sets. G and B0 through Bk are all disjoint finite sets. Every n in G is good. It will be in our introenumerable set. Every n in any of the bad sets is bad, and it will not be in the introenumerable set. Let A be the union of all of the good and bad, all the elements of the good and bad sets. Our labeling is going to map A cross the power set of A to almost an ordinal. Omega times 2 union this funny symbol. Okay, and basically it's going to tell us, it's going to tell, here, let me, it tells, LNC tells us how close we are to adding n to psi of C. Well, okay, we're not going to add n to psi of C. So this is not quite what I meant. I mean, as we grow C, how long is it going to be before n enters psi of the set that we're growing? The labeling is telling us that by well, first of all, if the labeling hits 0, that's equivalent to n being in psi of C. This funny symbol, which notice it looks like infinity from, if you're looking at it from the left, but it doesn't if you're looking at it from the right, and that's exactly perfect. This is going to be a large finite number, so large as to look infinite if you're on the finite side. And so we order these elements of omega times 2 union that symbol, as you would expect, but putting that symbol between the finite elements and the infinite elements. So it just stands for some large, it's a placeholder for some large finite number. Okay. Now, if D is larger than C, then, well, I want to say that the labeling that D puts onto N has to be less than the labeling that C puts onto N. We have to drop that labeling so that as we grow our set C, eventually we're going to hit 0, and we're going to put N into psi of well, our eventual D. That's the idea. Well, of course, this can't always be true. It's not true when you hit 0, you don't go any further down. And also, it's possible to hit that placeholder and just stay there. Well, that's bad behavior if we're trying to force N to eventually enter C. So we don't allow that behavior. Yeah, that allows us to sidestep the fact that omega times 2 is well-founded. So we don't allow that behavior all the time. It's only allowed if N is worse than any element of C. If I let AJ be the good sets union all the kind of higher bad sets, the bad sets BI for I greater than J, then we can, if C labels N with a placeholder, then for some J, N is in BJ, but C is a subset of AJ. So C looks good from the perspective of N. And conversely, well, not quite conversely, if C looks good from the perspective of N, well, then C thinks N is a bad element. We don't want to force it ever into psi of C. So the labeling has to be greater than or equal to the placeholder, the large finite placeholder. Okay, so that's the placeholder is letting us basically use a labeling for all the good and bad elements, but not force any bad elements into psi of our set. No bad number can be in psi of G, where and there's one more property, and it's a transitivity property, which says that if C union D labels N finitely, and every element of C is labeled by D finitely, then D labels N finitely. Okay. This just happens to be the exact right version to get the proof to work of the transitivity property that you could presumably right in much more generality than this, but let's not. All right, so that's the forcing notion. What is extension? I mean, that's what a condition is. What is extension? It is, I think, what you would guess at this point. If you're here with me right now, following along, it's what you would guess. The good set grows. You can't grow bad sets. You can add new bad sets, and the old bad sets remain the same. And the labeling has to, anything that was already labeled has to keep the same label. If we have a filter, the union of all the good sets for conditions in the filter is our I. And if F is a sufficiently generic filter, then I sub F is infinite. That requires some proof even. That's how bad this is, but not a lot of proof, but that's how bad this is. You have to actually show that you can't get stuck with these conditions. But it's not that bad. I is uniformly introenumerable. This is actually not hard because we built that in with the labeling and the definition of psi and the relationship between those two. And it does not have cototal degree. That's where the real work is being done in the proof. And am I supposed to end when? Okay. Okay. Well, I only have the next slide. I want to say very little about this last point, but I do want to explain why we have a sequence of bad sets. So I have some condition P, and I want to extend it to make progress towards my set I that I'm building not being cototal. I'm going to diagonalize against some witness that is cototal. So what I do is I put some new X into the good set carefully. This is a careful extension, such that no matter how I extend P0 to some P1, and what's this extension going to do? Basically, this extension is going to say, well, I put X in, and I want to diagonalize against cototality using X. Oh, shoot, I can't lock that in with the extension to P1. All right. So P1 is any extension, but really, for us, it's going to be an extension that locks in that we can't diagonalize using X in G. Well, there's another condition, Q0, not an extension of P0 or P1, but related to it, that puts X into the bad set, into a bad set. And this is still an extension of P. And Q0 is defined in such a way that no matter how I extend, so what I've done is I've actually taken P1, I've taken some of that good set and put it into a new bad set. Now that new bad set from the perspective of the elements of the old bad sets might as well be good. That's how that labeling nonsense was defined. So the labeling is going to really try to respect X being good with respect to the old bad elements, good enough-ish with respect to, well, the elements of the new bad set, and again, still good enough with respect to the good elements. In the sense that no matter how I extend Q0 to Q1, I can dump that new bad set back into the good set and get an extension R of P1. Just to be clear, here there exist an extension such that for all extensions, there exists an extension here, such that for all extensions, there exists an R. So there exists for all, there exists for all, there exists. And this R is going to basically combine this P1 and Q1. P1 will witness that I can't use X to diagonalize against cototality if it's in the good set. Q1, I can't use it to diagonalize against cototality if it's out of the good set. And R will give me a contradiction. But it's basically the fact that I can put X into a new bad set, taking the extension and then dump that bad set back into the good set, do a little relabeling to that placeholder, and get this R. That's why I need a sequence of bad sets, or I don't know, need. And that's why we use a sequence of bad sets. All right, and that's definitely all I want to say. So don't ask any questions. No, I'm joking, clap. just told them not to, though. That was a bad strategy.
So in symbolic dynamics,
Yeah.
what do you want to do with this?
What do I want to do?
Minimal shifts. I mean, if you have like a good equivalence or no, I mean, how would what would be the next step if you could substitute the minimal subshift by something else?
Well, I'm not sure. I mean, for them, I mean, I think that one of the things they wanted to know, I have my own. One of the things I think they wanted to know was whether every minimal subshift had a least complicated element. And that's, I mean, that I think even before our work, they knew that. I think what Emmanuel Jeandel wanted to know is, could we have just not done that construction and asked you first? So I'm not sure what kinds of questions they want to know, but yeah, if you're interested in the complexity of elements of a minimal subshift, then I mean, it depends on the kind of questions you have. I do think that though, I think the main thing we told him was that there were non-total, that some of the degrees of these things were non-total. And once he knew that, he was, you know, I'm not sure he wanted to know more. We answered a lot of questions he didn't want answered.
Comments or questions? Or maybe somebody online, which we haven't
Oh, we haven't looked at that.
seen.
No.
Okay. Okay. Thank you very much, Joe. We have a few minutes to move to the next talk.